Okay, good morning to all of you. Today we discuss further details on UPFC. Okay. Once again, good morning to all of you. We'll discuss UPFC in detail in today's class. Already we have discussed the operating principle and schematic we have seen. Just we'll go to the review of that again and we'll discuss further. Okay. See, to know the basic operation of the Qpfc, this diagram is very important. Here, the entire Qpfc is taken as a simple synchronized voltage source. You can see that the entire Qpfc is represented as a simple voltage source. Even for load flows also, just a fictitious loop, a additional node will be formed with this Qpfc, and remaining things are similar. Then in this Qpfc, mainly the series converter will inject a voltage, that is VPQ, which is in series with the transmission line, so that the effective the voltage at this one that is sending end becomes Vs plus VPQ, and this voltage is controlled in the entire region. Please, okay, see here the voltage is controlled for 0 to 360 degrees, and this magnitude is also controlled. So this is about the functional diagram of Qpfc is concerned. Then coming to the next one, that is actual schematic of this Qpfc. So that is okay, this one. So this is main diagram of Qpfc. So here in Qpfc, already we have discussed, we'll have two converters, converter 1 in series and converter 2 in parallel. Okay, converter 1 in parallel and converter 2 in series, and they are coupled back to back using this DC capacitor. Okay, so this is AC side of converter 2 converts DC to AC, and this is the AC side of the converter 1 and converts DC to AC, and real power flow is takes place from converter 1 to 2 or 2 to 1. It is a bidirectional. Please remember, as per the real power flow is concerned. And then the reactive power is controlled independently here at this node and also at this point. Okay, that is the advantage of Qpfc. So even if you see the Qpfc, static synchronous series compensator, there also we control this series voltage, but the difference between that Qpfc and this Qpfc is that it has one more converter, and here independently we are controlling the reactive power at this bus. So that is the advantage of this Qpfc or Qpfc. Qpfc means generally it will compensate only like series compensator capacitor. Okay, like that it will compensate. But here you will have all the possibilities. Shunt compensation is done, and also series compensation is done, like capacitor, variable capacitor, or like Qpfc. Okay, so that is the advantage. How? Just by controlling the injected voltage here. So here the voltage VPQ is controlled from 0 to V maximum as per the magnitude is concerned, and the voltage phase angle is controlled from 0 to 360 degrees. Okay, so that is about some basics of Qpfc. And then you can see that for any circuit, power circuit is not enough. We should have control circuit to generate firing pulses for these converters, so that the reference we consider it as that is V reference. Generally, this is used to control the voltage regulation. Z reference, series capacitive compensation is done. So for that, reference is given. Then sigma reference, that is phase shifting regulation, is takes place so that reference is giving. Then reactive power compensation, how much reactive power is required to compensate, that also we have to give. These are the reference values. Then coming to the actual, that is okay, current, voltage, and other powers that we have to measure. Okay, real power, reactive power, all these we have to measure from the basic circuit diagram. So different quantities we are measuring from the power circuit diagram, and these are all fed to this control circuit. And other parameter setting is also done, uh, required for the these things. Okay, so once you go to the detailed control block, there you will have PI controllers and other which is used to control the voltage of this capacitor voltage, and many other, that is the voltages of this one converter 2 and voltages of converter 1, and all these things will be there if you see the complete control blocks. But here we don't have that complete control block. We have only this one. Okay, so that is about the basic schematic diagram is concerned regarding UPFC, and operation is simple. So it is injecting voltage so that the reactance is the series reactance is controlled, voltage is controlled, and also the phase shifting is also controlled using this one. So here by injecting a voltage, and real power, reactive power is controlled independently for the converter 1 and converter 2, and this is the operation of this UPFC is concerned. Then coming to the next one, so that is the next last class we have discussed some control capabilities of this one. Okay, so there are three control capabilities of this UPFC. They are voltage regulation control, and second one line impedance control, third one is phase angle shift control, and fourth one, it is combination of all these one. That means simultaneously this all will be done at the same time. That means independently you can control, and also we can control all at a time. Okay, we'll see one by one. Last class I have drawn these diagrams and explained. Okay, again we'll see. So here this voltage at that series voltage is controlled, that our power system voltage is controlled by injecting voltage in series or or in phase or out of phase. So once you inject in phase, its voltage increases, or out of phase, its voltage decreases. You can see that simply. So the different for different values of delta V, that is the voltage that you are applying. You can see that. Sorry. Okay. So here the voltage injected, that is VPQ, is of in phase or out of phase. So that voltage is controlled from this point to this point, this voltage. So that's why here plus or minus is given. This V is controlled in this case, and in phase and out of phase is taken. Then coming to the second diagram, here the voltage is maintained by injecting a voltage which is in quadrature with the current. So here you can see that the current you have to consider. So it is at an angle. Okay, the voltage injected is at an angle 90 degrees with respect to the current. You can see that here the current, the voltage injected is 90 degrees. Okay, that is leading. Okay, so here the voltage is controlled. Sorry. Okay, the voltage is controlled just by injecting voltage in series or out of phase, in phase, out of phase. That is the first one. Voltage regulation is done here. Okay, then coming to the second one, that is line impedance control. Either capacitance effect or the inductive. In both of these cases, okay, the nature of the voltage. For example, if you consider in the case of capacitor, voltage is lagging by 90 degrees with respect to the current. So here the current voltage injected is lagging. So current is leading. So if you consider this one, voltage is lagging with respect to this current, and then if you consider this voltage and it is leading. So inductive effectance you get from this one, and capacitance to effect you get from this the other, okay, other one. So this way you get the inductive and capacitive effects in this case. Okay. So that is the series capacitive compensation. That is the second one. First one is voltage regulation. Just we are changing the voltage magnitude. Okay, in this case, we are injecting the voltage VPQ in such a way that it will be perpendicular to the current, How you can see that here different values of VPQ for capacitance and inductance were given. Okay, so by that way, you can change the series compensation. That means whatever discussed till now, that is okay, in series compensation, we have discussed about series capacitor, GTO control series capacitor, thyristor control series capacitor, thyristor switched series capacitor, that we have seen. So then in this case, okay, in the third case, just phase shifting is phase shifting. Magnitude won't change. Please remember that in this one, only the phase angle shift sigma you get in this case, in the third case. That is phase shifting is possible in this case. How you get this phase shifting? You can see that this is the tip of actual sending voltage, that is V. So once you inject VPQ, okay, in this way, then this phase shift is induced. Okay, this phase shift, that is, it is moving closer to the receiving end. Or if it is opposite, if you inject voltage in such a way that it is opposite, then phase shift increases and then power flow increases. So depending on this nature of the sigma, that is positive or negative, phase shift is introduced or reduced, and so that real power flow. Once you see that between sending end and receiving end, based on the voltage phase angle difference, the power flow will be takes place. Once you even the voltage magnitudes are same, the change in will be there in okay, phase angle difference. Because of that one, real power flow will take place, and that real power flow depends on the phase angle difference. Okay, that alpha, okay, whatever we have seen, EV by X into sine the alpha we are taking, okay, phase angle difference, or delta if you want to take, just only the representation is different. So these conventional control capabilities are very important as per the facts controllers are concerned. So then coming to this one, in this case, all three are done. One, voltage regulation, that means voltage is increased. And then second one, so that is series capacitive compensation is done. That means in this way we are injecting. And then third one, so that is phase shifting. So by injecting a voltage here, or this phasor, V phasor, change it to this one, okay, we just by adding VPQ. So in that you will have all the possibilities. That means the voltage is changed, the series compensation is possible, and phase shifting is also possible with this one. So all these three are possible with this facts controller. So that is UPFC, in particular UPFC. So this diagram is very, very, very important, and we'll explain the function of these different control capabilities with these diagrams. I'm repeating: voltage regulation, and second one is line impedance control. Third one is phase shifting. Very simple to draw. So here just we are representing different values of delta V, which is injected in phase or out of phase. Here along this line, what is this line? Which is perpendicular to this current one. Why? In case of series capacitive compensation or inductive compensation, only the voltage and current nature are getting by using this one. How? In case of capacitor, current is leading by 90 degrees. In the case of inductor, current is lagging by 90 degrees. So by injecting voltage, any of these voltage, we get the either series capacitive compensation or the inductive compensation. And 90% of the transmission lines are inductive, or we never get the capacitive. Only shunt capacitance sometimes dominate in a long lightly loaded transmission line, so that you get parental effect. There also we use shunt compensators, that is inductors, to compensate the voltage, not the capacitor. Generally, series series inductors are not used to compensate the transmission line, that is reactive power. We use either series capacitor or shunt capacitor or shunt inductor to compensate that. Inductor to compensate, not the series inductor. Even whatever may be the case in currently affected light loaded transmission line, we use these, that is the series capacitor. Never, for theoretical purpose, we discuss about series compensation of the inductor, but we never do, because 100% transmission lines are inductive in nature. Series inductance you will have, not the capacitance. Shunt capacitance, sometimes it charging current exceeds that voltage drop in the series inductor, so that you may have the possibility of current effect, that is receiving end voltage greater than 0. That too only special conditions, lightly loaded long transmission line. So that case it will happen. In all the normal loading or normal transmission line, you never get the voltage greater than the sending end voltage. Okay, so that's why we never use this type of that is inductive compensation. Okay, series inductive compensation. We use a series capacitive compensation, so that you get this way. Okay, that is voltage lags by current. Then coming to the third one, already discussed. Okay, phase shifting. In our syllabus we don't have phase shifting, static phase shifting transformer, but in actual facts subject, if you see that this is also coming to picture, because the power flow in the transmission line without compensator is given by Vs into Vr. Though they are equal, you get power flow. So this is Vs into Vr by X into sine delta. Vs into Vx by sine, okay. Vs into Vr by X into sine delta. This is ideal case we are considering. Practically some differences may be there. So it depends on the sending end voltage, receiving end voltage, reactance of the transmission line, and the sine delta, phase angle difference between these sending end and receiving end. This is changed. Now we consider it as a, okay, a sigma plus or okay, so delta plus or minus sigma you are considering. So this is the phase shift is introduced in the system. You can see that this sigma is introduced here, either positive or negative. You can see that you can increase, decrease. That means power flow, real power flow is controlled. You can increase or decrease the real power flow, so that by injecting, okay, the phase angle difference only, whereas the all other voltages are similar. You can see that if you consider V, that is either sending end voltage or receiving end voltage, or you may take it as both are same. Vs is equal to Vr is equal to V. If you consider, okay, here you can see that only after, even we are injecting a Vpq value, the phase, the magnitude of this V is same, but only it is shifted by angle sigma, or further if you go to the negative, that is minus sigma. So that difference will be increases. Difference between that is sending end and receiving end voltage increases, so that power flow increases. So that we have to see when you come across the power flows. Okay, so that three cases are done. These diagrams are very, very important. That's why I'm repeating again this in this one. Okay, so then, okay, we'll move to the how real and reactive power flows are controlled. So we'll move to that one. So I will explain these equations. Some people may feel it as a very difficult one, okay, but don't take it as that one. Okay, without controller compensator, without controller, we have done the derivation for the power flows, that is the real power flow, Vs into Vr into, okay, Vr by X into sine delta. Number of times I did derivation. Again, we do that derivation or a simple modification for this compensator. Okay, so even if these voltages are same, you get it as a V square by X into sine delta. So V square by X into sine delta. So this is the power flow without controller, So sine delta. Okay, delta varies. We are assuming that delta varies from 0 to, okay, pi. You are assuming sine pi is equal 0, sine 0 is equal 0, sine 90 is maximum. You get this one. So here I am representing the power flow without compensator, that you get the sinusoidal term. Okay, sinusoidal term. Then how this one, that is UPFC, will have effect on this one once you inject VPQ in series with the transmission line, that is in particular the UPFC. Okay, see here just we are injecting, I am repeating, redraw this diagram. Okay, here we are injecting a voltage VPQ in series with the transmission line, so that in place of sending end voltage you have Vs plus VPQ. So once you want to calculate the current in general without compensator, if you consider Vs minus Vr by Jx, okay, without compensator, the current flow is simply potential difference. Potential difference is nothing but simply Vs phasor minus Vr phasor divided by reactance, nothing but impedance. Okay, this is okay the current. Okay, this is the current. Now in place of Vs we have added UPFC, that means VPQ. Vs plus VPQ you get. In place of Vs you get Vs plus VPQ phasor. So this is the difference that you are getting once we add UPFC. So without UPFC, this is current is nothing but simply potential difference by the impedance, and this, if you multiply with the voltage, you get the a complex power, that is S, and that we take it as a P plus JQ. And if you take complex conjugate, P minus JQ becomes a VI conjugate, that we do the derivations for PQ, and already we did for without compensator. Okay, and we have calculated without compensator, we got V square by X into sine delta. Number of times we have seen power angle curve we have drawn number of times, even while discussing about the transient stability, we have taken electrical power as V square by X into sine delta, that is PM into sine delta, and the mechanical power we have taken, and we analyzed the transient stability using equal area criteria method. Now we are considering with UPFC. Okay, with UPFC, only the difference you get is that additional term you have, that is VPQ. Once you introduce here the additional term, one more term you get, that is Vs into VPQ by Jx term. This is P minus JQ, you get as this one. Okay, and because of this additional one, you get this one additional. Okay, without that, simply these equations anybody can do. So additional terms you get. So by using this one, okay, by using this, okay, you can control. And if you consider maximum values of this one, V into VPQ by X value, V into VPQ by X value for both real and reactive power, that is controlled by changing this one. So that they have shown in the diagram. That's all. Okay. Additionally, that means by changing this sign also we can change depending on the angle, this angle. Okay. So this you can inject, that is real power flow, you can increase or decrease. Reactive power flow, increase, decrease, that depends on the angle, this angle. So just by changing this voltage magnitude, you can change this amplitude, and by changing this angle, you can increase or decrease, that is plus minus sign you can take from this one, just by changing the angle. That effects you will have in the next diagram. Okay, you can see that. So here in this one, how real and reactive powers. So this is without compensator, you will have the reactive power, this one. So this already we have discussed a number of times. Okay, so this is without compensator. Now with compensator, that is UPFC, you can increase or decrease the power by this value. You can see that. Okay, and for the entire range for alpha, okay, that is from 0 to this pi degrees, you can vary the power plus or minus. That is possible with this one. So you can control the power over the wide range, and you can see that in this region we are controlling. Without that, you get this one. Similarly, at the cost of, that means reactive power is also controlled by using that one. Okay, so these terms we got in the previous expression, that is real and reactive powers, and their values also changed from 0 to pi value, minus and plus values. Okay, injected in phase and out of phase, that is also possible. Just alpha or the angle at which that injected will be different, so that you can okay, you can change the real and reactive power. So this way UPFC is okay capable of controlling the independently real and reactive powers. Okay, and further analysis are there. Okay, number of points are there, but you need not follow. Okay, and regarding the applications on the transmission line, okay, whatever discussed till now, okay, same again we'll discuss. Okay, this also you can add regarding the conventional transmission control capabilities of this UPFC, and also how real and reactive powers are controlled independently, and how they are controlled with that equations we have seen. That also you can add in the application part. Okay, so in this last chapter, sixth chapter, you have only UPFC, and in particular we have only schematic and principle of operation is one question, and the applications on the transmission line is the other one. So we use this one in the transmission line to control the real and reactive power, and at the same time we can, or how we are controlling this real and reactive power, by injecting a voltage in series with the transmission line. So this is done by mainly the converter 2. So main function of UPFC is done by the converter 2, whereas the converter 1 is to either supply the real power required by the converter 2, or it is independently controlling the reactive power at that particular node. So that is the advantage of this UPFC, and using this one, both real and reactive powers are controlled, and voltage magnitude is controlled 0 to maximum value. That depends on the rating of that UPFC, and also angle is controlled from 0 to 360 degrees. So the all functions, whatever we have seen till now, that is shunt compensation, series compensation, combined of this one, phase shift relay, even though that is not discussed, phase static phase shifting transformer topic is there, separate one in facts control, but we